What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. At Earth's distance from the Sun, every square meter turned straight toward our star receives about 1,360 joules of light each second. That is enough energy to make a dark surface painfully hot. It can power machinery, drive weather, and warm an entire planet. Sunlight is not weak when it reaches space near Earth. On May 14, 1973, that fact became an emergency. Skylab had launched into orbit, but the shield meant to protect the station from tiny impacts tore away during ascent. That shield had also been part of the thermal design. With it gone, direct sunlight began pouring energy into surfaces that were never supposed to see so much of it. The air inside the station approached 130 degrees Fahrenheit. Food, film, insulation, and equipment were at risk before the first crew even arrived. NASA did not solve the problem by heating the space around Skylab or cooling that space down. Astronauts deployed a parasol-like shade through an opening in the station. The thin barrier changed which surfaces absorbed sunlight. That was enough to pull the cabin back toward a usable temperature. Now move from Skylab to the Moon, only a short cosmic distance away. Near the lunar equator, ground under the long daytime sun can reach about 400 Kelvin, roughly 127 degrees Celsius. During the long lunar night, the same broad region can fall toward 140 Kelvin. Inside permanently shadowed polar craters, NASA's Diviner instrument has measured places near 25 Kelvin. Skylab overheated. Lunar shadows became colder than liquid nitrogen. Both occupied the same neighborhood of the solar system. Both were exposed to the same deep sky. The difference was not that one flew through hot space and the other sat inside cold space. The difference was the energy route. Sunlight is a stream of energy crossing emptiness. It is not warmth dissolved through a room. If the light strikes matter and that matter absorbs it, the matter gains energy. If the light misses, the vacuum does not collect the energy and become warm air. The light simply continues. That gives the first answer to the central question. Space can be flooded with sunlight without behaving like a sunlit atmosphere, because light does not need to warm the path it crosses. It needs something at the destination to absorb it. There are three familiar routes by which thermal energy moves. Conduction passes energy through direct contact. Touch a warm cup, and collisions inside the material carry energy into your hand. Convection moves energy with a flowing liquid or gas. Warm air rises, cool air sinks, and the room circulates. Radiation carries energy as electromagnetic waves. It crosses a vacuum perfectly well. Outside a spacecraft, vacuum removes almost all ordinary convection and almost all contact with surrounding matter. It does not remove radiation. In fact, radiation becomes the main external route left. So the phrase cold vacuum can be useful, but it can also plant the wrong picture. A vacuum is not an invisible refrigerated gas pressing against every surface. It is the absence of enough surrounding matter to enforce one common temperature through constant collisions. If the thought that sunlight is a delivery rather than a warm room is worth keeping, subscribe. It is a small way to help me make the next documentary. That correction opens a more interesting problem. If empty space does not carry one simple ambient temperature, what would a thermometer in space actually measure? It would measure itself. A thermometer is matter. Point it toward the sun, and it absorbs some fraction of the incoming light. Turn it toward Earth, and it can receive infrared radiation from the planet. Hide it behind a shield, and it sees a different sky. Electricity inside it may add heat. Its mount may conduct energy into or away from it. At every moment, it is keeping an account of energy arriving and energy leaving. The number it reports describes its own physical state after all those exchanges. It does not reveal a universal temperature belonging to the empty volume around it. This is easy to miss because thermometers on Earth usually sit inside matter. Air molecules strike the instrument from every direction. Those collisions bring the thermometer toward the temperature of the air. Put the same instrument in water, and the water does the same job much faster. The thermometer and its surroundings repeatedly exchange energy until their temperatures approach one another. Vacuum removes that crowd of colliding neighbors. The thermometer is no longer forced to join a common local temperature through air. It can still absorb sunlight, emit infrared energy, conduct heat along a support, and receive radiation from planets or equipment. But two thermometers a few centimeters apart can be designed to reach very different temperatures. One may be black and exposed. The other may be reflective and shielded. There is no surrounding air to erase the difference. The ordinary word temperature therefore needs a target. The temperature of what? Temperature belongs to a physical system. In a familiar gas, it relates to how energy is distributed among the motions of many particles. In a solid, energy also appears in vibrations of an organized lattice and in other microscopic states. In radiation, scientists can describe a spectrum with a temperature when that spectrum has the right shape. These are connected ideas, but they are not interchangeable labels for one cosmic thermostat. Heat needs equal care. Heat is not a material stored inside an object. It is energy in transfer across a boundary. An object has internal energy. It can gain energy from absorbed light, chemical reactions, electricity, collisions, or conduction. It can lose energy in other ways. When temperature difference drives an exchange, we describe that transferred energy as heat. This matters because the sentence "sunlight carries heat through space" can hide two different claims. Sunlight certainly carries energy. When a surface absorbs that energy, its internal state changes and its temperature may rise. But the light does not turn the empty root into a warm material. Transport is not the same as local thermal equilibrium. Imagine a sealed vacuum bottle holding hot tea. The empty gap between its walls suppresses conduction through gas and prevents convection. Shiny surfaces reduce radiation across the gap. The bottle does not preserve warmth because vacuum is cold. It works because vacuum removes two efficient roots, and the reflective walls weaken the third. Spacecraft engineers use the same logic at a much larger scale. They do not ask whether the surrounding vacuum is hot or cold and accept one answer. They list every route, how much sunlight arrives, how much Earth light arrives, which face sees darkness, how much electrical power becomes internal heat, where can that energy conduct, which surfaces can radiate it away. The design lives or fails inside that ledger. The sky itself adds another source. In every direction, space is filled with faint microwave radiation left from the early universe. The spectrum is extraordinarily close to that of an ideal thermal emitter at about 2.725 Kelvin. This cosmic microwave background is real. It is ancient light stretched to microwave wavelengths as the universe expanded. But saying that space is 2.725 Kelvin is a shortcut, not a complete thermal description. That number describes the brightness temperature of a radiation field. It does not force every atom, dust grain, planet, spacecraft, or patch of plasma to share that temperature. The proof is not merely philosophical. About 5,000 light-years away, gas racing outward from the dying star inside the Boomerang Nebula has cooled to roughly 1 Kelvin. It became cold enough to absorb some of the microwave background behind it. If 2.725 Kelvin were an uncrossable temperature floor for matter, that absorption could not happen. Rapid expansion did the cooling. The gas spent energy pushing outward, and its microscopic motions weakened. For a limited time and region, matter became colder than the ancient radiation filling the sky. The microwave background still matters. A perfectly isolated object, exposed only to that radiation, would exchange energy with it. But real objects are almost never exposed to only one thing. Starlight, dust glow, cosmic rays, nearby planets, internal power, and gas collisions may all contribute. Even deep space is an environment of several overlapping ledgers. The phrase temperature of space has the same problem as the phrase color of the ocean. It sounds like one question, but the answer depends on what is being measured, where, when, and by what interaction. That does not make the question meaningless. It makes it precise. Near Earth, the decisive source is the Sun. Its light crosses roughly 150 million kilometers before reaching our orbit. The crossing takes a little more than 8 minutes. Almost none of the energy is handed to the near vacuum along the way. The energy remains in the radiation until it strikes something able to scatter, transmit, or absorb it. The next question is therefore not why empty space fails to become warm. It is why different objects struck by the same sunlight do not all become equally warm. The answer is written on their surfaces. When a photon meets matter, several things can happen. It may bounce away, it may pass through, or its energy may be absorbed. Absorption does not mean a tiny parcel of warmth has entered. The electromagnetic field interacts with charged particles in the material. Electrons can move into different states. Atomic bonds and crystal lattices can gain energy. Through many internal exchanges, that added energy spreads among the motions available inside the object. The object becomes warmer when the new energy raises the temperature of the material. How much warmer depends on how much energy arrives, how much is absorbed, how much matter shares it, and how quickly energy leaves. That is why surface finish matters so much in space. A dark coating may absorb a large fraction of incoming sunlight. A bright metallic surface may reflect much of it. Yet dark and shiny are only visual hints, not complete thermal identities. A surface can behave differently at visible and infrared wavelengths. A coating that rejects much of the sun's visible energy may still emit its own longer wavelength thermal radiation efficiently. Engineers choose materials by measured absorptivity and emissivity across the wavelengths that matter, not by a simple paint chart. Absorptivity describes how readily a surface takes in radiation. Emissivity describes how effectively it sends out thermal radiation compared with an ideal emitter at the same temperature. Both can change with wavelength, angle, temperature, aging, and contamination. The useful lesson is not that black is always hot and white is always cold. It is that color and surface chemistry help control both sides of the energy ledger. Now follow the energy after absorption. Every object above absolute zero emits electromagnetic radiation. At temperatures familiar on Earth, most of that emission lies in the infrared. Human eyes do not see it, but thermal cameras do. A warm hand, a cold rock, the hull of a spacecraft, and the night side of a planet all send energy away as photons. Vacuum does not block this departure. No air is required. That is why radiation can both heat an exposed object and cool it. The rate of emission rises sharply with temperature. For an ideal emitter, total radiated power per unit area follows the fourth power of absolute temperature. This is the Stefan-Boltzmann relationship. Doubling absolute temperature does not merely double emission, it increases it 16 times. The fourth power creates a powerful stabilizing response. If an object absorbs more energy than it emits, its internal energy rises and its temperature tends to increase. The warmer surface then emits much more strongly. If the object emits more than it absorbs, it cools, its emission weakens, and the gap closes. Under steady conditions, the temperature can settle where incoming and outgoing power match on average. That state is radiative equilibrium. The word equilibrium can sound motionless, but energy never stops crossing the boundary. Sunlight continues to arrive. Infrared photons continue to leave. The balance is like a reservoir with a steady stream entering and another leaving at the same rate. The water level can remain stable while every molecule in the reservoir changes. Temperature is the level that closes the account. Geometry decides how the account is written. A flat plate facing the sun presents a large collecting area. Turn it edge on, and the intercepted power collapses. A sphere intercepts sunlight across a circular silhouette, but radiates from a much larger surface. A thin plate may radiate from one side or both. A rotating object shares sunlight around its body. A fixed object can keep one face illuminated and the other in shadow. The same material, at the same distance from the same star, can therefore settle at different temperatures simply because it has a different shape or orientation. This is visible in the clean dividing line between day and night. On an airless world, sunlight strikes one hemisphere. The other hemisphere sees no direct sun. If the material conducts heat poorly and the body rotates slowly, the two sides do not share energy efficiently. One surface can heat, while a nearby surface cools toward the deep sky. The moon makes this separation dramatic because it rotates once relative to the sun in about 29.5 Earth days. A point near the lunar equator spends roughly 2 Earth weeks in daylight and roughly 2 weeks in darkness. There is no substantial atmosphere to move heat from afternoon to night. There are no oceans to store energy and carry it across the globe. The upper ground is covered by regolith, a loose blanket of broken rock and fine dust made by impacts. Regolith conducts heat poorly, especially in vacuum. Sunlight can make the immediate surface hot, while deeper material remains cooler. When night arrives, the exposed grains radiate energy away and cannot draw replacement heat upward quickly. The result is not one lunar temperature. It is a map of surfaces, slopes, depths, times, and histories. Near the equator, the long day can push the surface toward 400 Kelvin. The long night pulls it far lower. At the poles, the geometry changes again. Some crater floors never see the sun because the moon's axis is only slightly tilted and the crater walls block the low solar angle. Those permanent shadows lose energy to a dark sky for immense spans of time. Diviner does not lower a household thermometer into those craters. The instrument measures infrared radiation arriving from the surface. The spectrum and intensity reveal a radiometric temperature. In Hermite crater, the observed values reached about 25 Kelvin. That number is not the temperature of the vacuum above the crater. It is the temperature of lunar material maintaining a very small outgoing infrared signal after losing access to direct sunlight. The moon also reveals the clock in the ledger. Suppose two surfaces absorb the same power for 1 minute. A thin layer of dust with little mass may change temperature rapidly. A massive block of rock can absorb far more total energy before its temperature moves by the same amount. Heat capacity measures part of that resistance to change. Conductivity decides how quickly energy can spread inward or arrive from below. Together with density, these properties create thermal inertia. Thermal inertia does not determine the final equilibrium by itself. It determines how quickly a material moves toward it, and how much memory the material retains from earlier conditions. Fine lunar soil responds quickly near the surface. Buried rock responds more slowly. During a lunar eclipse, diviner can watch different terrains cool at different rates. Rock stays warm longer than powder. The fading infrared glow becomes a map of material properties without anyone touching the ground. The surface is telling time with heat. This is why the hottest moment of a day often occurs after the sun reaches its highest point. Energy is still arriving faster than it leaves, so temperature continues rising. On Earth, late afternoon often feels warmer than noon. On a rotating asteroid, the warmest region can lie beyond the point, directly beneath the sun. That delay will later become strong enough to alter an orbit. For now, it explains why the phrase sunlight equals temperature fails. Sunlight supplies power. Temperature is the response of a particular system with a particular surface, shape, mass, route, and history. Move one of those terms, and the answer moves with it. Consider a polished foil and a dark ceramic tile floating side by side. Give them identical size and orientation. The foil may reflect most visible sunlight. The tile may absorb much more. But the rate at which each emits infrared energy can also differ. If the foil is a poor infrared emitter, even a small absorbed power can be difficult to reject. If the tile is an efficient emitter, it can lose energy strongly as it warms. One surface can run cooler because it rejects sunlight. Another can run cooler because it emits thermal radiation well. The best thermal coating may combine both jobs, low absorption at solar wavelengths and high emission in the infrared. This selective behavior explains the strange appearance of spacecraft. Gold-colored films, white blankets, black radiator panels, bare metals, and coated instruments are not decoration. Each surface is assigned a thermal role. The blankets commonly wrapped around satellites are made from many thin reflective layers, separated so that they touch as little as practical. The layers reduce radiation exchange and restrict conduction paths. They are called multi-layer insulation. Like a vacuum bottle, they do not create cold or heat. They slow selected routes. Radiator panels do the opposite. They are designed to see a cold portion of the sky and emit energy efficiently. Internal equipment conducts heat to them through structure, straps, heat pipes, or pumped fluid loops. The radiator then sends that energy away as infrared light. The radiator is not a grill dumping warm air. Nothing warm needs to blow past it. It is a carefully chosen surface making photons. These two strategies can exist centimeters apart. A blanket prevents unwanted exchange. A radiator encourages a controlled exchange. A heater adds energy when a component would become too cold. A shade blocks an unwanted source. Thermal design is not a war against the cold of space. It is traffic control for energy. That traffic can reverse within minutes. A satellite in low Earth orbit moves into sunlight and then into Earth's shadow. The sun disappears, but the craft still receives infrared radiation from Earth and may receive reflected sunlight from clouds or ground. Internal electronics continue producing heat. Some surfaces cool quickly. Others stay warm because they are insulated or connected to working equipment. No single outside temperature tells the spacecraft what to do. Now return to the lunar surface and compare it with Earth. Both worlds orbit at nearly the same distance from the Sun. Their sunlight differs only slightly at a given moment. Yet Earth's average surface temperature occupies a far narrower and warmer range than the Moon's exposed ground. The answer is not that Earth receives a private source of heat. The answer is that Earth has more routes, more storage, and more ways to delay the exit. About 30% of incoming solar energy is reflected back towards space by clouds, atmosphere, ice, land, and ocean. The rest is absorbed by the Earth system. The surface and atmosphere then emit infrared radiation. From far away, the planet's average outgoing radiation corresponds to an effective temperature near -20 degrees Celsius. But the average surface is closer to 15 degrees Celsius. The difference is produced by the atmosphere's interaction with infrared radiation. Gases including water vapor, carbon dioxide, and methane absorb selected wavelengths emitted by the surface. They then emit radiation in multiple directions, including downward. Energy still escapes to space, but much of the final emission comes from higher, colder layers. The surface must become warmer than the planet's effective radiating temperature to send enough energy through the complete system. This is the natural greenhouse effect. It does not create energy. It changes the altitude, wavelength, and rate at which energy leaves. Clouds complicate both sides. They can reflect sunlight and cool the system. They can also absorb outgoing infrared radiation and reduce immediate heat loss. Oceans add enormous heat capacity. Winds and currents carry energy from one region to another. Water changes phase, storing and releasing energy. Soil, vegetation, ice, and cities respond at different speeds. Earth has a complicated ledger. because Earth has a complicated body. Night on Earth, therefore, does not resemble lunar night. The ground loses energy, but the atmosphere radiates back toward it. Air moves, water releases stored heat. The clouds alter the view of the cold sky. A single night is short compared with the time required to drain the thermal energy of oceans and deep ground. The moon has no comparable blanket of moving air or global ocean. Its surface can see the sky directly and keep seeing it for roughly 2 weeks. So the sun is not failing to warm the moon. The day side proves that it can. The violent swing comes from what happens after the photons arrive and after the sunlight leaves. The ledger has an income. It also has an exit. The climate belongs to the complete path between them. That same path can be built deliberately. During the coast from Earth to the Moon, Apollo spacecraft slowly rolled around an axis. Crews called it the barbecue roll. The name made the maneuver sound casual, but its purpose was exact. Continuous sunlight on one fixed side could create large temperature differences across the vehicle. Rotation shared the exposure. No surface remained the permanent afternoon face, and no opposite surface remained in endless night. The spacecraft did not rotate to average the temperature of space. It rotated to average the sunlight absorbed by its own skin. This distinction is the difference between a useful model and a dangerous one. If engineers treated vacuum as a cold bath, they might expect every external surface to be cooled in the same way. In reality, the sun selects a direction. Earth selects another. Internal equipment creates local sources. Shadow removes one input abruptly. The spacecraft must carry energy through itself before a chosen radiator can release it. Conduction, therefore, remains crucial inside a vehicle, even though vacuum surrounds it. Metals, fasteners, panels, pipes, cables, and fluids connect components. A computer can overheat beside a freezing instrument because the path between them is weak. An electronics box may need a conductive strap to a radiator. A battery may need insulation from a cold panel and a small heater during eclipse. Thermal control begins by drawing a map of contact. Heat pipes are one elegant route across that map. Inside a sealed tube, a working fluid evaporates near a warm component. Vapor travels toward a cooler region and condenses, releasing energy. A wick or similar structure returns the liquid. The cycle can transport heat without a mechanical pump. The external vacuum is not carrying the energy. A deliberately built internal system is moving it to a surface that can radiate. Other spacecraft use pumped fluid loops. Some rely heavily on conductive panels. Thermostatically controlled heaters protect propellant lines, batteries, cameras, and mechanisms. Louvers can expose or cover radiating surfaces. Coatings establish how each panel responds to sunlight and infrared emission. Multi-layer blankets isolate what should not exchange energy quickly. A working spacecraft is a city of separate climates. The importance of that phrase becomes clear in thermal vacuum testing. Before launch, engineers place hardware inside chambers where air is removed. Shrouds around the test article are driven hot or cold to reproduce important radiation conditions. Lamps or other sources simulate solar input. The test is not merely checking whether a machine survives cold emptiness. It checks whether the model of every route predicts the measured temperatures. Vacuum can make a component hotter than it would be in air because convection is gone. A box that cooled acceptably on a workbench may retain too much of its waste heat when no surrounding air can carry it away. The absence of air is therefore not automatically a source of cooling. It can remove cooling. That inversion is one reason the instant freezing image of space is so misleading. Put a warm object in cold air, and molecules strike it, collect energy, and carry that energy away. Add wind, and the exchange accelerates. Put the object in vacuum, and those collisions disappear. The object can still radiate, but the rate depends strongly on its surface area, emissivity, and temperature. A shiny insulated object can cool surprisingly slowly. A dark radiator with a wide view of deep space can cool efficiently. The vacuum itself is not choosing. Skylab demonstrated the incoming side of this problem. Losing the meteoroid shield removed protection from sunlight. The station's internal temperature rose, even though the surrounding region was routinely described as cold space. The rescue shade worked because a small change in geometry cut the absorbed solar power. Apollo demonstrated distribution. The roll prevented one side from keeping the full burden of sunlight. Modern spacecraft extend the same logic with active control, surface engineering, and detailed computer models. James Webb Space Telescope provides the most dramatic single picture of the result. Webb operates near the second Sun-Earth Lagrange region, far beyond the Moon, in a large orbit that keeps the Sun, Earth, and Moon in roughly the same direction from the observatory. Its infrared instruments must stay extremely cold. A warm telescope would flood its own detectors with the same kind of infrared radiation it is trying to measure from distant objects. The solution is a 5-layer sunshield, roughly the size of a tennis court. One side faces the Sun, Earth, and Moon. The telescope and instruments remain on the other side, facing deep space. The layers are thin and separated. Sunlight strikes the first layer. Much of it reflects away. Energy that is absorbed becomes thermal radiation and is sent sideways and outward. Each successive layer receives less. Separation restricts conduction. Angled geometry gives the radiation a path away from the observatory rather than straight through it. The sunward side can sit around 85 degrees Celsius, while the cold side remains near -233 degrees Celsius. These temperatures exist at nearly the same location. They are separated not by a different orbit, not by a wall of cold gas, but by material, spacing, orientation, and radiation. Webb is the central contradiction made into hardware. Space is full of sunlight on one side of the shield. The other side uses the openness of the sky as a radiative sink. The telescope becomes cold not because vacuum touches it with coldness, but because the design denies most warm sources a clear route in while preserving a clear route out. The cold side does not stop at one uniform temperature. Mirrors, structure, detectors, and electronics have different requirements. Most of the observatory cools passively by radiation. The mid-infrared instrument needs an additional cryogenic cooler to reach an even lower operating temperature. Again, location does not supply one answer. Imagine replacing the sunshield with clear glass. Visible sunlight would cross. Absorbing structures behind it would warm. Or imagine coating the shield with a material that absorbed strongly but emitted poorly in the directions available. The layers would retain more energy. geometry alone would not save the telescope. Every layer needs the right optical behavior and the right view. This is also why a shadow in space is not automatically a permanent freezer. Shade removes direct sunlight, but an object may still see a warm planet, nearby equipment, or a glowing shield. Internal electricity may dominate. A radiator pointed toward Earth can absorb enough planetary infrared energy to become less effective. A telescope pointed at the wrong warm structure can see thermal noise rather than the universe. Engineers use a quantity called view factor to describe how much one surface can exchange radiation with another through geometry. A radiator with a wide view of dark sky has a strong route outward. Place another warm panel in front of it, and that panel occupies part of the view. Radiation now travels both ways. The surface does not radiate into a magical drain labeled space. It exchanges photons with everything it can see. At ordinary spacecraft temperatures, the dark sky sends back relatively little thermal radiation compared with a warm radiator. That makes net cooling possible. But the exchange is never one-sided in principle. The cosmic microwave background, stars, dust, planets, and neighboring hardware all contribute some incoming radiation. The word cold sink is therefore functional. It identifies a direction in which a system can reject more energy than it receives. It does not mean empty space is a block of ice. There is another engineering surprise. A spacecraft can be too cold and too hot at the same time. Sunlit solar arrays may run hot. A shaded fuel line may freeze. An operating processor can create local waste heat. An optical detector may require cryogenic conditions. Batteries often prefer a narrow, moderate range. Mechanical joints may seize if lubricants or materials leave their design window. A thermal system has to connect some regions, isolate others, add heat here, and release heat there. InSight, the Mars lander, used multi-layer insulation, painted radiator surfaces, sensors, heat pipes, and redundant thermostatic heaters to keep key electronics within their allowed range. The Martian atmosphere adds some convection, but it is thin, and the mission still depends heavily on radiation and controlled conduction. Farther from the sun, incoming solar power weakens with the square of distance. Double the distance, and the same sunlight spreads across 4 times the area. Solar heating falls, but internal radioactive or electrical sources can remain important. Heaters become mission lifelines. Radiators cannot simply be made larger without risking excessive cooling during quiet periods. Close to the sun, reflective shields, strict pointing, and heat-resistant surfaces protect spacecraft. Far away, insulation and internal power protect them from losing too much energy. The physics does not change. The size of each entry in the ledger changes. That is why thermal design can control mission geometry. A spacecraft may have to keep one side aimed at the sun. A radiator may need a protected view. A maneuver may be delayed until batteries or propellant reach safe temperature. Instruments may alternate use, because running them together would exceed the ability to reject waste heat. Temperature becomes an operational resource. Skylab's parasol, Apollo's slow roll, Webb's layered shield, and a small heater wrapped around a valve all solve versions of the same problem. They decide where radiation can land, where conduction can carry the result, how long energy can remain, and where infrared photons can escape. The more perfectly the surrounding vacuum removes accidental contact, the more deliberately the machine must manage every remaining path. Human beings add a moving, sweating, heat-producing body to that machine. The common image says an astronaut exposed to space would freeze instantly. The true thermal problem begins in almost the opposite direction. A human body continuously produces metabolic heat. Inside a spacesuit, air provides pressure and oxygen, but it also creates a sealed environment where moisture and heat can build. Outside the suit, vacuum cannot blow that heat away. Sunlight can add energy to the suit. Earth can add reflected and infrared radiation. The astronaut's own body keeps generating more. NASA suits use a liquid cooling and ventilation garment worn close to the body. Water flows through narrow tubes and collects heat by contact. The portable life support system then manages that energy, along with humidity and carbon dioxide. The white outer layers reflect much of the sunlight and protect the pressure garment from thermal extremes and tiny impacts. The suit is not a winter coat against a universal cold. It is a personal spacecraft, balancing pressure, oxygen, moisture, sunlight, metabolism, insulation, and radiation. Without pressure, exposure creates immediate dangers that have little to do with becoming a frozen statue. There is no breathable oxygen. Low pressure allows body fluids at exposed surfaces to vaporize more readily. Gas expands. Consciousness can be lost quickly from lack of oxygen. The body would also exchange thermal radiation, but freezing every tissue would take time because the body contains substantial mass and vacuum removes convective cooling. This distinction does not make exposure safe. It makes the hazard accurate. Even inside a functioning suit, thermal comfort is active work. An astronaut facing the sun may receive strong radiation on the outer garment. The shadowed side may see mostly dark sky. Rotation, posture, nearby structure, workload, and cooling flow all change the balance. A person drilling or climbing produces more metabolic heat than a person waiting. The same environment can demand cooling during work and heating during inactivity. Once again, the thermometer belongs to the object. The object now happens to be alive. This correction returns us to the moon with a sharper question. If sunlight can overheat machinery and people, why do lunar shadows become so cold? Because removing the largest income does not remove the exit. In permanent shadow, direct solar power falls to nearly zero. The surface continues emitting infrared radiation. Some energy arrives from nearby illuminated slopes, scattered light, warmer subsurface material, and the faint sky, but the total can remain very small. Over time, the ledger drains until emission weakens enough to match those limited inputs. The temperature falls because radiation is still working. Cold is not something the vacuum supplies. It is what matter approaches when its outgoing routes remain open and its incoming routes become weak. This principle reaches beyond machines and crater floors. It decides whether an atmosphere survives, whether water can remain liquid, and whether a world shares heat between day and night. The next object in the ledger is not a spacecraft. It is an entire planet. A planet receives sunlight across the disk it presents to the star. That is its collecting face. Yet a rotating planet can emit infrared radiation from a much larger surface. Atmosphere and ocean may carry energy away from the illuminated region before it leaves for space. Clouds may reflect part of the incoming light. Gases may absorb part of the outgoing infrared radiation and return some of it downward. The ledger has become global. Begin with the simplest imaginary world. Give it no atmosphere, no internal heat, a surface with one known reflectivity, and enough time for absorbed sunlight to balance emitted infrared radiation. Its average equilibrium temperature depends mainly on the star's brightness, the world's distance, the fraction of light it reflects, and the area across which the absorbed energy is redistributed. Each of those words hides a decision. Brightness at the planet is not the total power of the star. It is the power reaching each square meter at that orbit. As light spreads outward, the same total crosses spheres of increasing area. Twice as far away means 1/4 of the flux. 3 times as far means 1/9. Distance, therefore, changes the income quickly, but temperature does not fall in the same proportion. Emitted power responds to the 4th power of temperature, so equilibrium temperature responds more gently. A large change in energy flux becomes a smaller fractional change in temperature. Reflectivity changes how much of the arriving light enters the thermal account. A bright cloud deck can send much of the visible light back to space. A dark surface can absorb more. Yet reflectivity alone does not tell us the surface temperature, because the atmosphere may change how outgoing infrared radiation escapes. Redistribution changes where and when the energy leaves. A rapidly rotating world with a thick atmosphere can carry heat toward its night side and poles. A bare, slowly rotating world may keep most solar energy close to the place where it arrived. 2 worlds can absorb the same average power and still have radically different local temperatures. This is why the equilibrium temperature, quoted for a distant planet, is not a weather report. It is a model answer. It says what temperature a simplified radiating body would need in order to balance an assumed amount of absorbed starlight. Researchers must choose an albedo or estimate one. They must choose how effectively energy moves from day to night. They must usually leave out detailed greenhouse behavior until more information is available. The number is useful because it creates a common starting point. It is dangerous only when its assumptions disappear from the telling. Earth shows the gap clearly. Viewed from space, our planet reflects roughly 3/10 of the sunlight that reaches it. The rest is absorbed by atmosphere, land, and ocean. To balance that absorbed energy with outgoing infrared radiation, Earth as a whole has an effective radiating temperature near -20 degrees Celsius. The global average surface is much warmer, near 15 degrees Celsius. That difference does not mean Earth violates radiative balance. It means the surface is not the altitude from which all infrared energy escapes directly to space. Water vapor, carbon dioxide, clouds, and other infrared active material absorb and emit radiation. The surface and lower atmosphere can remain warmer, while the planet still sends the required power outward from higher, colder layers. The greenhouse effect does not manufacture energy. It changes the route and the temperature structure required for energy to leave. Picture a relay rather than a lid. Sunlight enters mainly at wavelengths for which the atmosphere is relatively transparent. The surface absorbs energy and emits infrared radiation. Some travels directly out through clearer spectral windows. Some is absorbed by gases and clouds. Those materials emit infrared radiation, both upward and downward. Energy eventually escapes, but the surface must reach a warmer state than it would have without those interactions. NASA estimates that without Earth's natural greenhouse effect, the global average surface would be near -18 degrees Celsius rather than about 15. Now compare Mercury and Venus. Mercury is much closer to the Sun. At noon, near its equator, its bare surface can become intensely hot. Yet Mercury has almost no substantial atmosphere to move that energy around or slow infrared loss. Its long nights become extremely cold. The planet displays a huge local swing because income is concentrated and redistribution is weak. Venus is farther from the Sun than Mercury, and its bright clouds reflect a large fraction of the sunlight. A simple glance at distance and reflectivity might suggest a cooler surface. Instead, Venus has the hotter average surface. Its massive carbon dioxide atmosphere and thick clouds create an enormous greenhouse effect. Solar energy that is absorbed must ultimately leave as infrared radiation from high in the atmosphere. The surface below is compressed beneath a deep atmosphere and remains hot enough to melt lead. Winds move heat so effectively that the contrast between day and night at the surface is modest compared with Mercury. One receives stronger sunlight, the other retains a far warmer, lower atmosphere. This comparison destroys the idea that distance alone sets temperature. It also destroys the idea that a reflective planet must have a cool surface. The full answer needs the optical properties of the atmosphere, its mass, the pressure structure, clouds, circulation, rotation, and the wavelengths through which radiation can escape. The Sun provides the income. The planet decides the bookkeeping. Even that sentence needs one refinement. A planet does not decide in any conscious sense, and the ledger is not a single box. Every altitude, latitude, material, and wavelength participates in a connected network. Energy can change form, move, wait, and leave from somewhere else. Ocean stores sunlight and releases it later. Air carries latent energy when water evaporates and releases it when vapor condenses. Ice reflects more sunlight than dark water. Clouds both reflect incoming sunlight and interact with outgoing infrared radiation. Mountains lift air. Rotation organizes winds. Continents interrupt currents. Temperature is the visible result of this traffic. Consider a planet that always turns the same face toward its star. One hemisphere receives continuous daylight, the other receives none. Without an atmosphere or ocean, the day side may become scorching, while the night side loses energy toward the sky until it is bitterly cold. Near the boundary, the star hangs close to the horizon. Add an atmosphere and the answer changes. Air warmed on the day side expands and rises. Pressure differences drive flow. Winds carry energy toward the dark hemisphere. Infrared radiation cools the air and surface. The pattern may form a fast, high-altitude current or broad circulation cells. If the atmosphere is dense enough and absorbs infrared radiation effectively, the night side can remain far warmer than a bare rock would. The same stellar flux can therefore produce either a brutal day-night split or a more even climate, depending on the world's ability to transport energy. Astronomers sometimes infer that ability from infrared observations taken as a planet moves around its star. The combined light of star and planet changes with orbital phase. If the planet's hottest region points toward us before, during, or after the fully illuminated phase, the timing and size of the infrared variation reveal how winds and thermal inertia move heat. This is a temperature map made without resolving the planet as a disk. But again, the measured radiation is not a thermometer floating in empty space. It is light from material. The instrument separates wavelengths and times. Scientists compare that pattern with models of clouds, chemistry, circulation, and surface properties. Every claimed temperature belongs to a method. A star has an effective temperature inferred from its spectrum and total radiation. A planet may have a brightness temperature at one wavelength that differs from its physical temperature at another depth. A gas can have rotational, vibrational, or kinetic temperatures describing different populations of motion. Under equilibrium, these measures may agree. Outside equilibrium, they may not. The phrase "temperature of space" has no place to attach to this diversity. It can refer to the cosmic microwave background. It can refer to the kinetic state of sparse gas. It can refer to the equilibrium of a particular object under an assumed radiation field. It can refer to what an instrument reports after it absorbs photons. These are related, but they are not interchangeable. Return to the question about a thermometer between Earth and the Sun. We can now make the answer more exact. Suppose the thermometer is a small black sphere. It absorbs sunlight from one direction and emits infrared radiation in every direction. Its equilibrium temperature follows from that geometry. Replace it with a flat plate facing the Sun, and the collecting area compared with emitting area changes. Turn the plate edge on, and direct solar absorption falls. Polish the front and it reflects more. Add a shiny screen between it and the Sun, and the screen changes what it sees. Place it close to a warm spacecraft, and infrared radiation from the spacecraft enters the balance. There is no reading until the instrument is specified. Now let the thermometer rotate. If internal conduction is strong, its temperature may remain fairly uniform. If the surface is insulating and the rotation is slow, a hot region can follow the Sun while the dark side cools. If rotation is rapid, heat may spread through time even when it cannot spread well through material. This introduces the next term in the ledger, not just how much energy arrives or leaves, but how long the object remembers. Thermal inertia is the resistance of a material to temperature change. It depends on properties that include conductivity, density, and heat capacity. A material with high thermal inertia can absorb substantial energy without changing temperature quickly, and it can keep releasing stored energy after the external heating falls. A material with low thermal inertia follows the changing input more sharply. Walk from dry sand to a large stone after sunset. The sand can cool quickly while the stone remains warm. The comparison is imperfect because air and moisture matter on Earth, but the memory principle travels well. On the Moon, fine regolith is an effective insulator. The upper surface responds strongly to daylight and darkness, while temperatures become steadier with depth. At a shallow level, the heat wave of each lunar day is already delayed and reduced. Farther down, short cycles fade, leaving longer-term averages and internal heat flow. This is why a surface temperature is not a whole world's temperature. A thermal camera measures radiation emerging from a limited depth and wavelength range. On a dusty body, that depth may be extremely shallow. The afternoon surface can be hot, while material just below remains cooler. Before dawn, stored heat below may flow upward and slow the final cooling. Scientists use these patterns to infer what a surface is made of. A field of exposed rocks stays warm differently from fine dust. Porous material conducts differently from solid material. Ice beneath a dark coating can change seasonal behavior. Boulders, craters, slopes, and shadows create a patchwork. Temperature becomes a remote sensing tool. Lunar diviner maps do more than identify hot and cold places. By following the surface across local time and season, researchers can estimate rock abundance and thermal properties. An unexpectedly warm night region may contain exposed blocks that retained daytime energy. An unusually cold region may be well shielded from warm surroundings or contain highly insulating material. The coldest reading is therefore not merely a record, it is evidence about geometry and matter. Rotation turns thermal memory into a directional effect. A place on an airless body is often hottest after local noon rather than exactly at noon. Incoming sunlight peaks first. The surface continues gaining more energy than it loses for a while, so temperature peaks later. The same lag makes the warmest part of Earth's day usually arrive after the sun is highest. The delay can push more infrared radiation from the afternoon side of a rotating asteroid than from its morning side. That small imbalance can change an orbit. Sunlight carries momentum. When an asteroid absorbs a solar photon, that momentum enters the body. When the warmed surface later emits infrared photons, those photons carry momentum away. If emission were perfectly symmetric in every direction and at every time, the pushes would cancel. Thermal memory breaks the symmetry. Imagine a rotating asteroid whose surface warms as it turns into daylight. The hottest region does not sit exactly beneath the sun. It appears later on the afternoon side. That region emits slightly more infrared radiation. Photons leaving in one direction give the asteroid a tiny recoil in the opposite direction. The push is far too small to notice during one rotation. It is far too small to feel during one orbit, but it repeats year after year. On a small asteroid, the accumulated change can shift the orbit enough to matter. This is the Yarkovsky effect. Its direction depends on rotation. For an asteroid spinning in the same sense as its orbit, the afternoon recoil can add a small forward component and gradually expand the orbit, reverse the spin, and the effect can shrink the orbit. Shape, surface roughness, conductivity, density, rotation rate, and orientation all change the result. Sunlight has become a thruster with no engine. The engine is delay. NASA's tracking of the asteroid, Bennu detected this thermal force by measuring its position with extraordinary precision over many years. The spacecraft visit then improved knowledge of Bennu's mass, shape, surface, and thermal properties. Those measurements help researchers project the asteroid's future path. This is not a decorative correction to orbit calculations. For a near-Earth asteroid, a small change accumulated over decades can alter where the body passes during a later encounter. Gravity still dominates. The thermal push is tiny. Precision requires both. The effect also sorts small bodies across the solar system. It can move asteroid fragments toward orbital resonances, where repeated gravitational interactions redirect them. Some eventually become near-Earth objects. A warm afternoon on a spinning rock can participate in a journey that lasts millions of years. Now the tidal question has acquired an unexpected answer. Space can seem cold because vacuum offers no warm material contact, and because an object can radiate energy toward a dark sky. Yet the same radiative exchange can create enough recoil to reshape an orbit. What looks like weak cooling is an unbroken traffic of momentum. An infrared photon does two jobs in this story. It removes energy and carries a push. The amount of recoil depends on where the photon leaves. A perfectly uniform sphere at uniform temperature would produce no preferred direction. A real asteroid has craters, rocks, slopes, and shadows. Sunlight enters cavities and scatters. Neighboring surfaces exchange infrared radiation. Roughness can concentrate emission directions. Dust and boulders store energy for different lengths of time. The thermal ledger is also a navigation model. This gives us a practical reason to resist the phrase cold emptiness. Emptiness is not doing the work. Surfaces are absorbing, conducting, storing, rotating, emitting, and recoiling. The fewer molecules there are to smooth the pattern by contact, the more clearly the properties of each surface matter. There is a second reason. Not all sparse matter in space is cold at all. Between planets and stars, there are particles. Some regions are extremely thin, yet the particles can move at enormous speeds. If temperature is inferred from their velocity distribution, a dilute plasma can be assigned a very high temperature. This sounds like the opposite contradiction. How can a place be extremely hot if it would not quickly heat a person or machine? Because temperature and heat transfer are not the same quantity. Temperature describes an energy distribution per particle or per active degree of freedom. Heating an object requires a flow of energy into that object. A gas with very few particles can give each particle tremendous energy while carrying little energy per cubic meter. Collisions with a surface may be rare. Radiation may dominate the object's thermal balance instead. Imagine one fast grain of sand crossing a vast room. Its speed can be high. The room is not, therefore, full of enough moving material to warm a wall. Add countless grains, and the energy density changes. The analogy is limited because plasma particles carry charge and interact with fields, but it isolates the missing factor. Individual energy does not tell us how many energy carriers arrive. In Earth's upper atmosphere and surrounding plasma, instruments can report particle temperatures far above the melting point of ordinary materials. A spacecraft does not instantly melt because the density is low, the particle distributions are complex, and its total heat balance includes sunlight, infrared emission, electrical power, and other sources. Near a star, the outer atmosphere can have particles at temperatures of millions of degrees, while the visible surface below is only thousands of degrees. That fact belongs to plasma physics and energy deposition, not to a universal hot room around the star. We do not need to solve the heating of stellar atmospheres here. We need only protect the definition. A high kinetic temperature in sparse plasma does not guarantee a high rate of heating for a solid object. The reverse is also true. A radiation field can heat an object even where there is almost no matter to possess a gas temperature. Sunlight crosses vacuum and delivers energy at the absorbing surface. Matter, temperature, and radiation temperature are different ledgers that can exchange entries. Inside a sealed oven, radiation, air, and walls may approach a common thermal equilibrium. Their temperatures become closely related. Space is usually not such an enclosure. Radiation streams from different sources with different spectra and directions. A detector may see the sun in a tiny part of the sky, a warm planet across another region, stars elsewhere, and the microwave background behind all of them. There may be no single blackbody spectrum that describes the whole view. Call the sun a radiation source, with a photospheric temperature of roughly 5,800 Kelvin. That does not mean a distant object becomes 5,800 Kelvin. The sun covers only a small angle in the object's sky. Its radiation is diluted across distance. The object absorbs according to area and wavelength, then emits according to its own area, temperature, and surface properties. A tiny bright source and a vast dark sky can coexist in the same view. This is the geometric heart of the original contradiction. The sun is hot, sunlight is present. Yet the sun occupies only a fraction of the directions into which an object can radiate. A surface facing the sun can collect concentrated power from that direction, while the rest of the object sees much weaker surroundings. Balance decides whether the object warms, cools, or stays steady. There are places where even the phrase dark sky needs care. A low-orbiting spacecraft sees Earth across a large fraction of its view. Earth reflects sunlight and emits infrared radiation. A craft near Jupiter may receive radiation from the planet and its environment. A dust cloud can glow in infrared. A spacecraft inside a warm enclosure can exchange radiation mainly with the enclosure rather than with distant space. The sky is part of the hardware. Engineers draw these views as surfaces and angles. Astronomers reconstruct them as spectra. Climate scientists average them across a planet. The mathematics changes scale, but the central question remains the same. What can this object see, and at which wavelengths? That question explains why a polished emergency blanket works. Its thin material does not contain a large reservoir of warmth. The metallic surface changes radiative exchange. It reflects much of the infrared radiation that a warm body would otherwise lose to cooler surroundings. On Earth, it also alters convection by trapping a layer of air, but in vacuum, the radiative role remains. The question explains why multi-layer insulation looks like crinkled foil. Multiple reflective layers separated by spacers reduce radiation transfer across the blanket. If the layers were pressed into strong contact, conduction would bypass part of the design. If the outer surface had the wrong solar properties, it could absorb excessive sunlight. The question explains why radiators are often white or specially coated rather than simply black. The word black in everyday color is not enough. A useful surface may need low absorption of solar wavelengths and high emission at its own infrared wavelengths. Those properties can be engineered separately because sunlight and thermal radiation occupy different parts of the spectrum. The question explains why a shiny metal left in sunlight can remain cooler than a dark coating, yet a shiny internal surface can make it harder for stored heat to escape. Color is a wavelength story. Now return to the cosmic microwave background. Its nearly perfect blackbody spectrum corresponds to a temperature of about 2.725 Kelvin. It arrives from every direction because it is ancient radiation filling the observable universe, stretched to microwave wavelengths by cosmic expansion. If an ideal object were isolated from every star, planet, dust cloud, collision, magnetic process, and internal source, and if it exchanged radiation only with that background for a very long time, it could approach the background's temperature. Real objects carry complications. Radioactive decay can add energy. Chemical reactions can add energy. Tidal flexing can add energy. Collisions and cosmic rays can add energy. Dust and starlight add radiation. A surface may emit poorly at the relevant wavelengths. A cloud may expand and cool faster than the background can restore its energy. The Boomerang Nebula provides the dramatic example. Gas rushing outward expanded so rapidly that it cooled to around 1 Kelvin in some regions. It absorbed microwave background radiation behind it, revealing that it was colder than the background brightness. This does not overturn the cosmic measurement. It clarifies what that measurement is. 2.725 Kelvin is not a police barrier below which matter is forbidden to travel. It is the temperature of a pervasive radiation field. A system out of equilibrium can be colder for a time if a process such as expansion removes energy faster than the background returns it. Laboratories can also cool selected degrees of freedom far below the cosmic background through active techniques. Those systems are not passively equilibrated with the sky. They use work, isolation, lasers, magnetic fields, evaporation, or other controlled processes to direct energy elsewhere. Cold is an energy history, not a substance. The universe itself has a thermal history. In its early dense state, matter and radiation interacted frequently. Expansion stretched radiation to longer wavelengths and lowered its characteristic temperature. The background we measure now is a cooled remnant of that earlier era. Stars later created local islands of intense radiation. Planets, dust, gas, and black holes process energy in different ways. The universe can have a low background temperature and still contain stellar interiors at millions of degrees. Thin plasma with high particle temperatures, cold molecular clouds, warm dust, and human-made detectors held close to absolute zero. One cosmic average cannot replace a map. That point matters when a documentary image paints space blue and frosted. Blue is a visual convention. Frost requires molecules to condense onto a surface. An object in vacuum does not acquire ice merely because it enters shadow. It needs a source of vapor, a surface cold enough for that material to stick, and conditions that let the deposit remain. Water ice in permanently shadowed lunar regions is evidence of delivered or locally produced water molecules finding cold traps where sunlight cannot readily drive them away. The vacuum did not manufacture the ice. Geometry helped preserve it. On a spacecraft, contamination can move from a warmer surface to a colder one. Materials release small amounts of vapor. Those molecules travel through vacuum and may condense on a cold optical element. Thermal engineers and contamination specialists work together because a very successful cold surface can become a collector. The same absence of air that prevents convection gives loose molecules an open path. Again, vacuum is not nothing in the practical sense. It is a condition that removes some interactions and exposes others. There is another way for matter to carry energy without becoming hotter. It can change phase. Ice exposed to vacuum does not need to pass through a pool of liquid before becoming vapor. Molecules can leave the solid surface directly. That departure requires energy. Sunlight absorbed by a comet can therefore be divided between warming the material, conducting heat inward, emitting infrared radiation, and freeing molecules from ice. The temperature may remain near a phase-controlled range, while substantial energy goes into the transformation. This is why a comet is not simply a cold rock that warms smoothly as it approaches the sun. Its surface is a changing landscape of dust, ice, pores, shadows, and active vents. Sunlight reaches different slopes at different angles. Heat penetrates only so far during each rotation. Volatile material beneath the surface can turn to gas. That gas moves through pores and can lift dust into a surrounding coma. Energy becomes motion and phase change. As the comet rotates, an active area moves into and out of sunlight. Gas production rises and falls, with a delay set by the depth and thermal properties of the source. Jets can push on the nucleus and alter its spin or orbit. Once again, sunlight becomes a mechanical influence through an uneven thermal response. Not every patch behaves alike. A dark dust layer may absorb sunlight and insulate ice below. A fresh icy patch may reflect more light. A cavity can trap radiation exchanged between its walls. A steep face may receive only glancing sunlight. Material can collapse and expose a new source. Asking for the comet's temperature would erase the process. We need temperatures of particular surfaces and depths, measured or modeled at particular times. We need gas production, composition, illumination, and thermal inertia. The useful answer is a field, not a single number. Far from the sun, an icy body can remain active if it contains substances that vaporize at lower temperatures, or if internal transformations release energy. Closer in, water ice becomes more influential. The transition depends on pressure, composition, structure, and history. The energy ledger predicts activity more faithfully than a label such as frozen. Phase change also protects and threatens spacecraft. Propellant must remain within a workable state. A liquid line can freeze. A cryogenic fuel can boil away if insulation and venting fail. Water from a human system can condense on a cold surface. Lubricants can change behavior. Batteries can lose performance without becoming permanently damaged, or suffer damage if pushed beyond their allowed thermal range. Temperature limits are often material limits. Thermal expansion adds another consequence. Materials change size as temperature changes. If two connected materials expand by different amounts, joints and optical alignments can move. Repeated transitions between sunlight and shadow can cycle stress. A mirror that must hold an exact shape cannot be treated as a generic warm or cold object. During an eclipse, a satellite can lose solar heating quickly while continuing to radiate. When it returns to sunlight, exposed surfaces warm again. The body does not respond instantly. Different components have different thermal inertia and different views. Engineers must check not only the highest and lowest eventual temperatures, but also the gradients and rates of change. The dangerous quantity may be the difference across a structure. Pouring energy into one face while the other remains cool can bend a panel. Rapid change can crack a material even when neither side exceeds a simple temperature limit. Optical systems may require a period of settling after a maneuver because the structure must approach a stable thermal shape. This is another reason the first thermometer question was incomplete. One sensor cannot report a gradient. A network of sensors can still miss a small hotspot. Models divide the machine into nodes and calculate radiation and conduction between them. Tests place hardware in vacuum chambers with controlled radiant sources and cold walls. Engineers compare predictions with measurements and refine the model. The chamber does not reproduce infinite space. It reproduces the important exchanges. Its walls are cooled to create a low infrared background. Lamps or heated panels imitate the sun. The test article operates, moves where possible, and generates internal power. Sensors reveal whether a radiator, heater, blanket, joint, and electronic box behave as expected. The walls matter because radiation always needs a view. A chamber with warm walls would send more infrared energy toward the spacecraft, even if the air had been removed. Pumping out gas alone does not create the thermal environment of deep space. Vacuum and cold are separate test conditions. This detail is easy to miss because a thermal vacuum chamber performs both at once. The vacuum suppresses convection. The cooled enclosure creates a dimmer radiative environment. The solar simulator adds directional incoming energy. Together, they reproduce the ledger relevant to the mission. The same separation appears in a household insulated flask. Vacuum reduces conduction through gas and eliminates convection across the gap. Reflective walls reduce radiation. A stopper limits conduction and circulation through the opening. If any one route dominates, improving another route may produce little benefit. Thermal control is the art of finding the dominant path. Sometimes the dominant path changes during the mission. A spacecraft may be warm while its engines operate and cold during a quiet coast. A lander may receive sunlight during the day and depend on heaters at night. Dust can settle on a radiator or solar array. A coating can darken under radiation. Fuel use changes mass and internal geometry. A planned instrument duty cycle can become impossible after another component fails. The ledger is alive even when the machine is not. Internal energy can dominate far from sunlight. A radioisotope power system releases heat as unstable nuclei decay. Part of that heat becomes electricity, while the rest must be managed. In a cold environment, waste heat can protect electronics and instruments. It can also disturb a measurement if the instrument needs to sense faint infrared radiation. A world can likewise remain active through internal sources. Radioactive decay, leftover heat from formation, differentiation, impacts, and tidal flexing can keep interiors warmer than their surfaces. An icy exterior may hide a warmer interior. A planet or moon can emit more energy than it absorbs from the sun. Surface cold does not prove internal stillness. The path from interior to space may cross rock, ice, liquid, gas, and atmosphere. Convection can occur inside a body even when the exterior faces vacuum. Molten material can transport heat. Solid rock can convect slowly over geological time. Cracks and eruptions can create local shortcuts. The three heat transfer modes were never three separate universes. They connect in sequence. Energy can convect through an interior, conduct through a crust, and radiate from the surface. Sunlight can radiate to a panel, conduct into a coolant loop, convect with moving fluid inside the loop, conduct into a radiator, and radiate away again. Vacuum removes convection only where there is no fluid. It does not remove fluid inside a sealed system or beneath a planetary surface. That single clarification prevents another common mistake. Saying there is no convection in space is useful only when the subject is the external vacuum. Spacecraft cabins have air circulation. Liquid cooling loops deliberately move fluid. Stellar and planetary interiors contain moving material. Gas clouds can flow, shock, and expand. Location does not choose the mechanism. Matter does. Now consider how remote temperature measurements are made. Every object above absolute zero emits thermal radiation, but an instrument receives only a portion. A detector has a limited wavelength range, field of view, sensitivity, and calibration. Material between the source and detector may absorb or emit. Reflected sunlight may mix with thermal emission. A rough surface may send radiation in directions that differ from a smooth one. Scientists compare the measured spectrum with physical models. For an ideal blackbody, the spectral shape reveals a temperature. Real materials have wavelength-dependent emissivity. A brightness temperature is the temperature an ideal blackbody would need to match the measured intensity at a chosen wavelength. It can be extremely useful without being identical to the material's kinetic temperature. Earth's atmosphere offers a familiar example. At some infrared wavelengths, a satellite sees radiation emerging from near the surface. At others, gases are opaque, and the radiation reaching space comes from higher layers. Different wavelengths carry temperature information from different depths. A spectrum can be a vertical map. On an airless body, wavelength still matters. Minerals have distinct emission features. Surface roughness creates miniature slopes with different illumination and views. Fine grains scatter and emit differently from solid slabs. The observed signal across one camera pixel may combine sunlit rock, shadow, and dust. The instrument does not fail when it reports their combined radiation. Interpretation fails only if the mixture is mistaken for a single, literal surface. Contact sensors have their own complications. A probe attached to a spacecraft must conduct energy to and from the structure. Sunlight may strike the sensor housing. Wires conduct heat. The sensor can shade the very surface it measures. Good design and calibration make these influences known. Measurement is another object in the ledger. This is why exact claims require source discipline. A reported crater temperature may be a brightness temperature derived from infrared measurements under specific conditions. A spacesuit temperature limit may refer to material qualification rather than human comfort. A planetary average may combine a model and observations. A plasma temperature may describe particle motion rather than a contact reading. The number gains strength when its definition travels with it. Our original question can survive all this detail because it was never really asking for one number. It was asking how hot sunlight and cold outcomes can occupy the same universe. The answer is now complete enough to withstand measurement, material change, internal power, and time. There is one final boundary to mark. Passive cooling can only approach the balance allowed by the radiation and heat sources around it. If an instrument must become colder than that passive balance, engineers need active refrigeration. A refrigerator does not destroy heat. It uses work to move energy from a colder region to a warmer one, where a radiator can reject it. The cold stage absorbs energy from the detector. A compressor or another cooling mechanism drives the transfer. The warm stage must then dispose of both the detector heat and the work added by the cooling system. Colder operation can therefore create a larger rejection problem elsewhere. This is why a cryogenic instrument may sit behind elaborate passive shields before an active cooler begins its final task. The shields reduce sunlight and radiation from warm structures. Passive cooling lowers the starting temperature. Active cooling then handles the smaller remaining load. If the shield allows too much energy through, the cooler may not have enough capacity. The sequence follows the ledger. First, reduce income, then provide a path outward, then spend work only on the part that remains. Some astronomical detectors must be cold, because their own thermal motion and radiation would obscure faint signals. The objective is not to protect the instrument from a mythical freezing vacuum. It is to stop the instrument from outshining what it is trying to observe. A warm infrared telescope is like a camera, whose housing glows into its own lens. Cooling lowers that self-generated background. Shielding keeps external warm sources out of view. Stable temperature prevents a changing instrument signal from imitating a changing sky. Calibration then separates the remaining detector response from the astronomical light. The cold is part of the measurement. At the opposite extreme, a heater may be the simplest thermal control device. A thermostat senses when a component approaches its lower limit and switches electrical power into a resistive element. That heater turns electricity into local thermal motion. Insulation slows the loss. The system accepts a small energy cost to avoid a larger failure. Cooling and heating are not opposing mission philosophies. They are neighboring entries, managed toward different component limits. The best thermal design is rarely the coldest possible machine. It is a machine in which every part remains inside the range where its materials, electronics, fluids, optics, and people can do their work. We can now answer a series of apparent contradictions without changing the model. Why did Skylab overheat in space? Its protective thermal shield was lost. Direct solar energy entered too strongly, and vacuum could not provide convective cooling. A replacement shade reduced the income. Why can a permanently shadowed lunar crater reach temperatures near 25 Kelvin? Direct solar income is almost absent. Nearby warm views are limited, and the surface continues losing energy through radiation until the remaining income and output balance at a very low temperature. Why can Webb hold one side near 85 degrees Celsius and another near -233? Its layered shield controls reflection, conduction, spacing, and view, creating two different radiation environments at the same location. Why does an astronaut need liquid cooling? Metabolism and absorbed radiation create heat inside an insulated pressure system, while vacuum removes the ordinary route of external convection. Why is Venus hotter at the surface than Mercury? Distance and sunlight are only the beginning. Venus has a massive atmosphere that reshapes infrared escape and transports heat. Mercury is a nearly bare surface with extreme local cycles. Why can a hot dilute plasma fail to cook a spacecraft? High energy per particle does not guarantee many particles or a large heat flow. Why can infrared cooling move an asteroid? Photons carry momentum, and rotation plus thermal delay makes their emission asymmetric. Why can matter become colder than the microwave background? The background is a radiation field, not an absolute material floor. A system out of equilibrium can remove energy faster than the field replaces it. The answers look different because the objects are different. The accounting rules are the same. Incoming radiation, reflection, absorption, conduction within matter, convection, where fluid exists, storage, internal generation, outgoing radiation, geometry, time, change any entry and temperature changes. This model also tells us what not to ask. How cold is space has no complete answer without a location, an object, a timescale, and a measurement method. A better question is this: what temperature would this particular thing reach here, under these conditions? To answer, begin with sources. How bright is the star at this distance? Does a planet or nearby machine fill part of the view? Is there plasma or gas delivering particles? Is there internal electrical, chemical, nuclear, tidal, or metabolic power? Then examine the object. What wavelengths does it absorb? What does it reflect or transmit? How effectively does it emit infrared radiation? What area collects energy and what area can release it? Then inspect the roots. Can heat conduct into another region? Can a liquid or gas circulate? Is the object insulated? Does a radiator face dark sky or warm hardware? Then add time. Does it rotate? How quickly? What is its heat capacity? Is its surface dust, rock, metal, fabric, gas, or ice? Has it just entered shadow, or has it remained there for centuries? Finally, define the measurement. Is the reported value a contact sensor reading, a brightness temperature at one wavelength, a kinetic temperature inferred from particles, an equilibrium estimate, or a global average? Only then does the number mean what we think it means. The model is more demanding than the phrase, "space is cold." It is also more beautiful. It turns temperature from a painted backdrop into a physical story. A scorch mark reveals absorption. A delayed afternoon peak reveals storage. A cold crater reveals a missing view of the sun. A thin foil blanket reveals spectral design. A planetary climate reveals transport and infrared escape. A changed asteroid orbit reveals the recoil of photons that carried heat away. The universe does not label these processes for us. It gives us light, motion, matter, and time. Temperature is one way their history becomes visible. Now place the original scene in front of us one last time. At Earth's distance, sunlight crosses each square meter facing the sun with more than 1,000 watts of power. There is no atmosphere between the planets to become a warm room. The beam passes through until matter reflects, transmits, or absorbs it. A dark plate facing the sun may become hot. A reflective plate turned edge-on may remain much cooler. A shielded telescope with a clear view outward may descend toward cryogenic temperatures. A powered instrument behind that telescope may need a radiator. A grain of dust may heat and cool quickly. A boulder may remember daylight. A rotating asteroid may turn that memory into thrust. All occupy the same space. None has to share one temperature. This is why the title's two statements can both be true. Space is full of sunlight because radiation crosses the vacuum. Space can produce extraordinarily cold objects because the vacuum supplies no surrounding warm matter, and because an object with weak incoming energy can continue emitting toward a much dimmer sky. But the precise correction is worth keeping. Space itself is not cold in the way air, water, or metal is cold. Empty distance is not a material reservoir that pulls heat out by touch. What we call the cold of space is the thermal state of matter and radiation under particular conditions. The sun is not failing to warm space. Sunlight is traveling through it exactly as light can. Warmth appears where that energy is caught, shared, stored, and balanced against every route out. Skylab caught too much and nearly lost its mission. The moon's deepest shadows catch almost none and cool for ages. Webb separates those outcomes with 5 thin layers. Earth turns sunlight into an inhabited climate through oceans, clouds, air, ground, and infrared active gases. Bennu turns a delayed fraction into a tiny change of path. The microwave background sets a faint radiative glow behind them all, while an expanding nebula demonstrates that even that glow is not a universal floor for matter. There was never one temperature waiting in the darkness. There were only ledgers. Every surface keeps one. Every atmosphere moves one. Every instrument reads one. Every orbit slowly records one. The next time an image shows sunlight blazing through black space, do not imagine a hot beam inside a cold room. Imagine energy in transit. Ask where it will land. Ask what will absorb it. Ask what can carry it away. Ask what the object can see. Ask how long it remembers. Those questions turn the contradiction into a map. Space is not a cold room around the sun. It is the place where every object must keep its own account of light.